Hello everyone. In this video, we are going to learn about the complexity analysis. Algorithms, we are going to compare the program's complexity, right? When I talk about program's complexity, mainly I am talking about the two complexity. One is time complexity, another one is the space complexity. In simple way, you can say that it is the time required to execute a program. It's called time complexity. And whenever we talk about space complexity, it is the memory requirement of the program to execute the code, right? So when we run the program, the time complexity will depend mainly on the input size, mainly on the input size, okay, which usually we will denote by n, because when we take more input, it will take more time to execute. Let's take one example. Let's suppose I want to sort 10 elements and I want to sort 100 elements. If you compare two instances, then you will come to know that the time it will take in to sort 100 elements are more than the 10 elements. So obviously, more the size, more the time complexity and space complexity. So we can say that time complexity is basically the running time of the program. It's basically the running time of the program, right? So when you run the program, the time complexity will come in the function of n. Let's suppose you are running some program, or we can say algorithm. So if you run the algorithm, we can find out the complexity of that program. Okay. But today we are not going to find the time complexity or space complexity, but just we will analyze that what is the complexity and how do we measure the complexity and what kind of notations we are going to use for analyzing the complexity. Or sometimes we compare two algorithms, or sometimes we want to compare two algorithms. For that purpose also we use some asymptotic notation. We will come to that after some time. Okay, first, if I say you that when an algorithm is taking n plus 3 time, okay, n is the number of inputs and plus 3 maybe because of some other instructions, maybe for example printf or maybe return 0 or whatever. Okay, so any other functions or constant values can come also. Okay, but in n plus 3 I will look for the biggest order, biggest function, we can say. In that case biggest function is n, so I can ignore this plus 3 right now. Okay, so let's suppose for this function complexity is theta of n. Now, right now, you might be not knowing about the theta. Okay, we will come to this notation after some time in the video. Okay, so theta of n I will say. Okay, let's take another example. If I say n square plus 2n minus 3, in this case, again, complexity will be of n square. I will look at the highest function in the function. Okay, highest order we can say n square. Okay, so what I am ignoring 2n minus 3. Why I want to ignore? We are ignoring these constants because we are looking for this n to be a very big number. Okay, let's suppose it is n tends to infinity. Okay, we want to see the asymptotic behavior, we can say. Okay, means the value of n is very large. You cannot think of it that much large. Okay, so in that case when we see the growth of these functions, then n squares growth is very high as compared to 2n. That's why I can ignore 2n minus 3, right? Let's take another function, 4n plus log n. In this function also highest order will be of n only. Okay, I will ignore 4. I will ignore log n also. Okay, log n is too much smaller than n. Okay, so I will say the complexity of this function is also theta of n. So complexities will be represented like this with the help of some notation. Right now I'm using theta notation. Is that clear? Okay. So if I want to compare two functions, then you should be able to tell that which one is smaller and which one is bigger. Then only we can compare the time complexities. Right? So let's take one example. It is a constant. So whenever you come across any constant, complexity will be theta of 1. So this value, if you consider 7 lakh also, then we will consider this as a theta of 1. That is the least value you can say. Means irrespective of the input, we can solve the problem. Irrespective of the input, we can solve the problem in constant time, we can say. Right? So I can say 7,000 is the smallest one. I will denote it by theta of 1. After this, now you can see 4n minus 3 here and 4n plus 1 also, right? Both are having complexity theta of n, because I told you that we have to remove the constants, right? They are very small as compared to the value of n, and usually if I want to substitute the value, then I will consider n is equal to very large number. A very large number, usually I consider 2 raised to the power 100. Now, if you substitute this value, you can solve the log also. Easily you can solve the log functions also, right? That's why I have taken power of 2, because these logs are usually base 2. And even if it is base 3 also, it will not be a problem. Okay. So let's try one value and we will try to substitute that. Okay. If I take this log n and I will try to substitute here, I will get what? 100 log 2. So log 2 is a constant in this case. So I will ignore this, or log 2 by log 2, if you do it also, then it is 100 into 1. That's why it is 100. Yes. So log n is giving us this answer for the value n is equal to 2 raised to the power 100. Okay. If you compare this with the function directly n, if I want to compare with theta of n or the function we can say 4n minus 3, then the value of n, if you substitute, you will get 2 raised to the power 100, which you can say which is much bigger than the value of log n. That's why log n will come first, right? Log n will come first. After that, obviously what will come? N. N means both the function we have 4n minus 3 and 4n plus 1. Both are equal. You can write in any order. Okay. Either you can write 4n plus 1 before also, 4n minus 1 3 you can write after 4n plus 1 also. So both have same complexity theta of n. There's no constant here. Directly we can write theta of log n. Okay. Next. What will come next? Next is, if you are confused, n log n and n square, we can try this by putting some value. Okay. So if I substitute the value n log n, 2 raised to the power 100, what will come? Log n will become log 2 raised to the power 100, means it is 2 raised to the power 100 into 100, right? Now, if you substitute value n square, if you substitute n is equal to 2 raised to the power 100 here, you will get this value, and this will be equivalent to 2 raised to the power 200. Now you can see this is much bigger than the n log n. So n log n will come first, because it is smaller than the n square. Next will come is n square, obviously, that is theta of n square we can say. And last value will come is the exponential value, that is 2 raised to the power n. 2 raised to the power n is exponential. You write 2 raised to the power n, n's value, and it will come 2 raised to the power 2 raised to the power 100, which we cannot even think what will come. Okay, so which is much bigger than the remaining complexities, okay, or rest of the complexities. So in this way, you should be able to compare the functions first, that which function is bigger, which one is smaller, and which one is equal. Okay. Okay, check the question. Fn is equal to n square minus 4, gn is equal to n square plus n plus 1. Both the function have quadratic complexity, means n square is the highest order, means both are same. So which options will be correct? Yes, you're thinking that all of the above, then all are correct, because Fn is equal to big of Gn means it is less than is equal to. So is equal to is there, it means this equation also is correct. Fn is equal to omega of Gn, you are saying? Yes, in this case greater than is equal to is there. So is equal to means this is also correct. And theta obviously it is correct because it is exactly equal to Gn. So all of the above option is correct. Okay. In this question, we have three options. Okay. So you have to tell me which of the following is correct. First one, you can see Fn is equal to log n and Gn is n. So you can say that Fn is smaller. So you know that Fn is equal to big of Gn. So in this case, Fn is smaller. So it is correct or not? Yes, it's correct. Then opposite cannot hold because Gn is equal to big of Fn, I'm saying, then it is incorrect. Right? So this will not be your correct answer. Then Fn is equal to omega of Gn means Fn is bigger than Gn. No. So it is also not correct. So in this way, we can compare the two complexities using the asymptotic notations. Next, we will see about the asymptotic notations. The meaning of asymptotic is we want to see the big value of n. Okay, big value of n means if n tends to infinity, when the value of input is tending to infinity, then what is the behavior of the function? Right, that is actually the meaning of asymptotic notations. Okay, the notations mainly we have three notations. Okay, first notation is big O. Big O. Okay, this is called big O. So big O notation, let's suppose one example I want to take big O of n. Okay, another notation is omega. Okay, so it is denoted by this and we will write like this, omega. Another notation we have is theta that we have used in last slide. Okay, that is called theta of n. So what is the difference and why we use these all three notations? Okay, so whenever I talk about big O notation, it will show you the upper bound value. It will show you the upper bound value. Means the complexity should be less than is equal to n. Okay, means it will show you the upper bound means maximum value it will show. Okay, if I want to denote in the form of functions, then I can write like this. In this way, I can compare two functions with the help of big O notation. Okay, so big O notation, if I say that big O is there, then I will say that Fn is less than or is equal to G of n. Okay, so if I say that Fn is equal to n, Gn is equal to n square, then You can say that Fn is bigger of Gn, right? Next, if I want to show the lower bound, if I want to show the lower bound, then I can say that I'm looking for the minimum complexity. Okay, means the complexity of the program is greater than is equal to n. It will show you the lower bound or minimum value. Okay, so Fn is equal to, if I write omega of Gn, then simply you can say that Fn is greater than is equal to C into Gn. Okay, some constant also can come. So no problem if I add some constant also, not a problem. Okay, so let's take one example. Fn is equal to, let's suppose 4n, Gn is equal to, let's suppose it is 100. Okay, so you can see that this 100 is a means constant. It means it's theta of 1. Okay, this is the theta of n. So you can say which function is bigger? Obviously Fn. So in this case, I can say that Fn is omega of Gn, right? Next, theta. Theta is used for tight bound. Okay, tight bound means when the complexity is equal. When complexity is equal, Fn is equal to, let's suppose given is n square minus 3. Gn is also, it is equal to n square, maybe some other n square. Okay, so in this case both are having equal complexity, then I can say that Fn is equal to theta of Gn. So it may be possible that for some value the complexity will be bigger, and for some value complexity will be smaller. C2 into, okay. Overall, we can say it is a tight bound means the complexity is equal for both the function, or we can say growth of the functions are equal. Okay, means theta of n, if I'm saying, means I want to show the exact complexity, right? So let's take one example. Oh, let's take now another example by which we will understand that what is best case, what is average case, and what is worst case. So we are taking one problem where we want to search the element from the array. Okay. So if I want to search the element, so array will be given to you. Let's suppose array is given like this. Okay, I'm drawing in the blocks. In this array, we have, let's suppose, n elements. We are having total n elements. Now we have to search by linear search, means sequentially we will search. Okay, first I will check for 2, 3, 4. Okay, if I tell you to search 3, if I tell you to search 3, what I will start from, starting from index 0. Then I will search for index 1. Then I will found the element here. Okay. So in this case, we can stop here. We can stop here. Means this case is called best case. Why we are calling it as best case? Because we are finding the element at the initial position only. Or we can say we are finding the element at the constant position. Right? We are getting the element at second position itself. Even if we are getting the element at 100th position, then also we will say it is the best case. Why? Because 100th position is also a constant, and in the case of constant we write theta of 1. So best case will always be theta of 1. Okay, then we can have average case also and worst case also. In the first case, the complexity is theta of n, theta of n, theta of n. Why? Because if we search for n elements and if we find the element at the last position, or if we don't find the element at all, then we can say that we have to run through all the n elements, and loop will run from 0 to n minus 1, means n times it will run. That's why complexity will be theta of n. Now, in average case, what will be the complexity? It will be n and not n by 2, right? So average case complexity is also n, not n by 2. Why? Because in n by 2 is a constant. And if we take n is a very big value, let's suppose 10,000, if we divide it by 2 also, it will not matter a lot. It will be giving same answer. Okay, this is also a big number. This is also a big number. So in average case, also we will write theta of n. So another way in which we can use asymptotic notation to show the exact complexity of best case, average case, or worst case. If you don't want to say best case, average case, worst case, you can simply say the complexity of searching the element is big of n. Complexity is big of n means the complexity should be less than is equal to n. Okay. So this is the way in which we can use the asymptotic notations. Hope you understood everything from this video. Thank you for now.